Welcome to chapter 6.1. Now we shall continue with state the characteristic of a system in equilibrium. So the characteristic of a system in equilibrium is one, it must be in a closed system, means that nothing is added or removed. The rate of forward reactions equals to the rate of reverse reaction. Properties such as concentrations or pressure of reactants or products are constant. Equilibrium can be approached from forward and reverse direction, and final equilibrium position is the same. Okay, so for example, look at this. The equilibrium is reached when the rate of vaporization is equal to the rate of condensation. Next, interpret the curve of concentration reactants and products against time for reversible reaction. Okay, let's look at what does this mean. Now, we have reactant, we have product. Okay, so what happened is, let's look at the first one. The dissociation of N2O4 to NO2 starts with 1 molar and 2 molar. Okay, so for N2O4, the reactant, it starts with 1 molar, and then for NO2, okay, it starts with 2 molar. Okay, for B. Okay, so I will start with A first. Okay, for A, you can see this is reactant, so it is 1. The product, nothing is formed yet. That's why it is 0. Okay, now at equilibrium, okay, the concentration will be constant. Okay, so let's look at what does this mean. Let's Okay, this one is 0.8. Okay, for N2O4, okay, at certain temperature, when the equilibrium is established, it is 0.8. Okay, now let's say because we have reversible reaction, so now the reactant becomes product. So when the reactant becomes product, initially N2O4 is 0. So it will somehow reach, after sometimes it will reach equilibrium. So when it reach equilibrium, it is still 0.8. Okay, so no matter whether it is starting from 1 molar or it is a product increasing, at equilibrium, the concentration will be the same. Okay, now let's look for another one, that is NO2. Okay, NO2, like just now I mentioned, it starts from 0 because it is a product, nothing is formed yet. So when it reach equilibrium, it will be constantly 0.4. Okay, because this is reversible reaction, so now NO2 becomes reactant. So it starts with 2. When it starts with 2, reactant NO2 produce N2O4. So NO2 will slowly reduce, but when it reaches equilibrium, the concentration is also constant at 0.4. So you can look at this, whether the reaction starts with 1 molar or 2 molar, the same concentration of the two compounds result once equilibrium is reached. Okay, now let's look at another one. Okay, so let's say I label this as the reactant and O2 is the product. Okay, so when I start, let's look at this one. This one means that it starts with the product. Okay, so when it starts with product, start with the product initially is 0, so it will increase. Then N2O4 is the reactant, so reactant will slowly decrease. Okay, now next one, if we start with N2O4, okay, if we start with N2O4, it will slowly decrease. Okay, I think just now I mentioned something wrong. Okay, ignore what I say just now. Okay, I will restart again. Okay, I will start with this one first. Reactant N2O4, reactant it will slowly reduce until it reaches equilibrium. Then NO2 is the product. Product starting is 0 and then it will slowly increase until it reach equilibrium. It will be constant. Okay, now next one, what happened is, okay, we change another one, that is NO2 reversible becomes N2O4. So it will slowly reduce until it reaches equilibrium. Then N2O4 now becomes react. N2O4, okay, why this one is high? Why it is not zero if this is a product? Because in a closed container sometimes, okay, the process has started. Okay, the process has started, so we have both reactant and product. So the product is not equals to zero in this graph. So the product will still increase. Okay, now let's look at the next one, the third one. Okay, the third one is now N2O4 becomes a product. It's still the same. N2O4 becomes product. It will slowly increase until concentration becomes constant. Then the NO2 has now becomes a reactant. It will slowly reduce until equilibrium is reached. Okay, so now I just want to highlight again how to interpret from the graph. If you see it is increasing, means that this becomes product and this one becomes reactant. But the equation, we do not change the position. We only know that it is going forward or reverse. Okay, for in this case, it is going reverse reaction. Okay, it favors reverse reaction. For this case, okay, NO2 increase, so means forward. Okay, going forward. Then this one, NO2 decrease. NO2 decrease means it is reverse because N2O4 increase. So this is a reverse reaction here. All of them are reverse reaction. Only that whether it moves forward or move reversible until it is still the same until equilibrium is reached. All the position is the same. Okay, so let's look at this again. Whether the reaction starts with any concentration, okay, the same concentration of the two compounds result once equilibrium is reached. Okay, so that's all for the explanation for the graph for reversible reaction. And remember, reversible reaction occurs all the time. It does not stop or goes to completion.